All right. Hey, AP Chemistry. I wanted to make video notes that kind of end with what we've been doing in Unit 6. This is Unit 6 Important Information Part 1. We're going to talk about energy transfer and thermal equilibrium. Your job is to answer all of the questions in this notes packet that connect to what we've been doing in the lab, but I'm going to kind of talk it through. If you don't need me to explain about these things, you could go straight to answering and doing the sample problems. So the first thing that's very important in these notes is recognizing the difference between endothermic and exothermic processes. This was on your pop quiz. So if energy is released during a chemical or physical change, the reaction is called exothermic. So this is our system. Energy is leaving it, and it feels hot. Okay, and so here's another way of looking at it. Here's our system. Here's the surroundings. The surroundings are going to absorb energy. The system is releasing energy. And sometimes that's what's tough with recognizing whether it's going to be hot or cold, because we feel the surroundings. The surroundings feel hot for an exothermic reaction, and it's getting energy. Right? And that's kind of what I explained down here. In an exothermic reaction, energy is released and temperature of the surroundings increases. So examples of this, and it might be hard to recognize, but an example of an exothermic reaction would be like condensation. If I have gaseous water, it needs to release energy to become liquid water and energy. Sorry, I'm going into like the next part of my notes here. Okay? Or another example of an exothermic reaction is dissolving a solid and temperature increasing. Okay? So, kind of like in a hand warmer. All right, so those are just some examples. Or if I want to go on this condensation route, instead of condensation, I can also do freezing. And you could think of a refrigerator for this. Because a refrigerator on the outside feels warm. So freezing could be H2O liquid to H2O solid, and energy is released. Okay? And then the opposite is said about endothermic reactions. Endothermic reactions, the system absorbs energy. So since the system is taking in energy, the surroundings is losing energy. And the surroundings, sorry, that looks ugly. Surroundings feel cold, right? So since the system is absorbing energy, it's taking energy from the surroundings. The surroundings is losing energy. The surroundings is losing energy. The system is gaining that energy. The system is gaining energy, and the surroundings is going to feel cold. And so in an endothermic reaction, energy is absorbed, and since it feels cold, the temperature of the surroundings is going to decrease. And so examples of endothermic processes are the opposite of condensation. So boiling is an endothermic process, H2O liquid plus energy. I'm going to do right here, it becomes H2O gas. Okay, I kind of wrote it on the side. An ice pack is definitely an example of an endothermic process, because meaning like the one where you pop it, right? When you pop it, a solution forms and then it feels cold. That's because that reaction absorbed energy from the solution. Okay? So those are big examples of exothermic and endothermic and knowing between the two. There are some sample problems for you to understand and know and answer that are related to exothermic and endothermic processes. So work on those sample problems. Then on the next page, on page 3, we have energy diagrams. These top may look familiar. This one, if I have my reactants and they look like they're in higher energy than my products, it looks like my products are lower in energy. Products lower in energy. That means energy was released. That's what it says right here. Energy equals negative overall, delta H energy. This is an exothermic energy diagram. All right, we have to label that. So we saw this in Unit 5, so we talked about this. So exothermic is when the product's energy is lower than the reactants. It releases energy. And then, of course, if this is exothermic, then this is endothermic, because energy was absorbed. Delta H energy is positive. And we've already talked about delta H. Delta H is known as enthalpy. Enthalpy. It's the energy associated with a change. We're going to talk more about that in our part 2 notes. But delta H is enthalpy. Specifically, enthalpy is energy at constant pressure. That's not really important for AP chemistry and knowing that definition. But delta H is negative for exothermic processes. Delta H is positive for endothermic processes. We also saw heating and cooling curves in Unit 3. I'm going to just move this camera down a little bit. Oh, sorry. Okay. So here is a heating curve. Okay. We have a solid. On the angle, there's an increase in temperature. Increase in temperature. Increase in temperature. That means I'm increasing thermal energy. If this looks and sounds familiar for maybe if you've taken chemistry before or we've talked about this. So what this means is my particles move faster. Move faster. And also, as you can see at these segments, on the first segment, if this is water, this is 0. This is 0 degrees Celsius. If it's below 0, it's a solid. If it's if at 0, it freezes. If it's above 0, it's a liquid. And then this temperature here is 100 degrees Celsius. That's where it begins to boil. And if it's above 100 degrees Celsius, it's a gas. Okay? And then we have 2 parts here where temperature remains constant. And that's during freezing, melting, condensing, boiling. Those are known as phase changes. And we tap into phase energy. Okay? And so I wanted to draw and write these processes, right? So freezing and melting, if I have freezing, again, I'm H2O liquid. And to freeze, I need to release energy. I got to get colder eventually or lose energy. Freezing is an exothermic process. So that means energy is in the products plus energy. That's exothermic. Melting is the other way. All right. I could do melting. And melting is going from H2O solid. It's actually this flipped. Plus energy. I got to add energy. And I get H2O liquid. And that's endothermic. I'm only going to do one, but I'll do condensing, and then boiling is the opposite. Condensing for water, and this is going to happen at the boiling point or the condensation point. Condensing is going from H2O liquid, and it's got to release energy. Sorry, H2O gas, my bad. To H2O liquid, and energy is released. So that's exothermic. Okay? So it's very important to remember what happens at these processes. when there is a phase change, the particles are rearranging and they're going, if I'm going from solid to liquid, they're spreading apart. If I'm going from liquid to gas, because I'm going a phase change, they're spreading apart. If there's just a temperature change, they're just moving faster. And we're going to see, and you already kind of know, how to calculate for both of these. Okay? We could also have the opposite happen. Okay? Where I could have the cooling curve for water. Okay? Same idea. I start with steam, I have liquid, and then it goes to ice. Okay? This is an overall decrease in energy. And still, this angle curve is a decrease in temperature, or a change in temperature, decrease in thermal energy, and where there's going to be a way to calculate that. And you're going to see that it's Q equals MC delta T. We already know about that. And then I have constant temperature, because it's flat. A flat line means, this is a temperature versus time graph. So this is temperature, usually in degrees Celsius. Oops. My thing kind of, my bad. Temperature in degrees Celsius, and then time over time. And flat line means constant, so I have constant temperature. That means I have a phase change. And I didn't mention this on the previous page, but this is going to be a decrease in phase energy, which we're going to call that delta H. I'm going to write this on the previous page. This is phase change, phase energy. I'm going to say increase in phase energy. And we're going to call phase energy delta H, energy of a change. Okay? So now there are a couple of sample problems for you to do related to those energy or there's one problem actually related to calculating and looking at energy diagram. And I'm going to talk about heat transfer and thermal equilibrium and end this video, and then I'll make my next video on calculations. So if I have block A being at a higher temperature than block B, so I'm going to call this hot, and I'm going to call this cold in parentheses, and that's usually represented by red and blue. If they come into contact with each other, what's going to happen? Apparently, some energy is going to be transferred, and it shows the heat flow from the warmer block to the cooler block. When I have two objects coming into contact with each other at different temperatures, typically hot becomes cool and cold becomes warm until they reach the same temperature. And then when they reach the same temperature, they cannot transfer energy anymore. Cannot transfer energy. In order for there to be a transfer of energy between two objects, one of them has to be at a different temperature than the other. And so specifically what that looks like on a molecular level is my hot box has the particles moving faster. My cold box, the particles moving slower. Moving slower. When things are cold, they move slow. When they come into contact with each other, the hot particles collide with the cold. And so then the hot particles begin to slow down, and then the cold particles begin to speed up until they're all at the same speed. The same average, oops, can't see, that's spelled wrong. Average kinetic energy. So same temperature, same speed, same average kinetic energy. Sorry you can't see that. That word is average. A-V-E-R-A-G-E. Okay? So if I am at the same speed, I have the same temperature and the same average kinetic energy. If I'm hot, I have more KE. If I'm cold, I have less KE. Higher temperature, faster. Lower temperature, slower. And then they come into contact with each other, and then eventually they're going to reach the same temperature, have the same average kinetic energy, and the same speed. And so that is because energy will always move from hot to cold. Energy always flows from hot objects to cold objects. And I put cold in parentheses because cold just means I'm lacking energy. Okay? When this happens, this process here, or this space in which I reach the same temperature, the same average kinetic energy, and the same speed, this is known as thermal equilibrium. And if I were to plot a graph of these two objects, one of them would be at a lower temperature, one of them would be at a higher temperature, and the lower temperature one would increase, the higher temperature one would decrease until they meet at some common temperature. So hot, cold, and then there is the same temp. And I'm going to call this time, and then degrees Celsius. So I have my hot object, it's going to lose energy. Cold object's going to gain energy until they reach the same temperature. And this part here at the flat line is thermal equilibrium. Okay? So, when two substances at different temperatures come into contact, the higher temperature substance will lose energy via collisions. The lower temperature substance will gain energy via collisions, which is what we just said. What's very important here is the amount of energy lost will equal to the amount of energy gained. Q loss is equal to negative Q gain because of conservation of energy. And we've done and seen calculations with this where if my water got cooler, it's because some other object gained energy or got warmer. Right? If I had a situation like that, or if my water got warmer, it's because some other object got cooler. Q loss is equal to negative Q gained. So if I know that something lost 50 kilojoules, something else must have gained. So if something lost 50 kilojoules, something else must have negative 50 kilojoules, which becomes positive 50 kilojoules. Something else must have gained 50 kilojoules. And then when two objects come into contact and transfer energy until they reach the same temperature, we already said that that's known as, it's at thermal equilibrium. Okay, and I have diagrams here of that happening. Sorry if you couldn't catch that. I have high temperature, low temperature. There's transfer of energy between high to low. Particles are at different speeds, and then eventually particles are at the same speed. There's thermal equilibrium, and there's a net heat transfer. And then here's another example. I have cold water and a hot object, Q1, Q2. Right? Let's just say heat. The cold object has a small amount of heat. The hot object has a large amount of heat. When I transfer, energy is going from the hot object to the cold object. And then eventually they reach the same temperature. Now, if this hot object had 500 kilojoules, and this cold object had 10 kilojoules, and then the hot object transferred 400 kilojoules, the water would gain 400 kilojoules. So the hot object would lose 400 kilojoules. The cool object would gain 400 kilojoules. Q loss is equal to negative Q gained. Okay? All right. So with that information, there are a bunch of more sample problems for you to work on. Sample problems 5 through, oh, I have 2 7s. Oh no. 5 through 9. And in my next video, I'm going to talk about the calculations required for energy changes according to temperature and phase changes.